As we've seen throughout the course so far, in Nest.js applications, everything has its place. This structured application organization helps us manage complexity and develop with solid principles. This type of organization is especially useful as the size of our application or team grows. Keeping code organized, establishing clear boundaries, and having dedicated architectural building blocks, all with a separate set of responsibilities, helps us make sure that our application remains easily maintainable and scalable over time. In Nest.js, we have 4 additional building blocks for features that we haven't showcased yet. These are exception filters, pipes, guards, and interceptors. Exception filters are responsible for handling and processing unhandled exceptions that might occur in our application. They let us control the exact flow and content of any or specific responses we send back to the client. Pipes are typically useful to handle 2 things: transformations, meaning to transform input data to the desired output, and validation, meaning to evaluate input data and, if valid, let it pass through the pipe unchanged, but if not valid, throwing an exception. Guards determine whether a given request meets certain conditions like authentication, authorization, roles, ACLs, etc. And if the conditions are met, the request will be allowed to access the route. And lastly, interceptors. Interceptors have many useful capabilities inspired by the aspect-oriented programming technique. Interceptors make it possible to bind extra logic before or after method execution, transform the result returned from a method, extend basic method behavior, and even completely override a method, depending on specific conditions. For example, handling something like caching responses. So now that we've covered the basics, let's dive into all 4 of these new building blocks in the next few lessons. Before we jump into the specifics of each Nest building block, let's take a step back and talk about a few approaches we can take to bind any of these building blocks to different parts of our application. Basically, there are 3 different ways of binding filters, guards, and interceptors to our route handlers, with a bonus 4th way that's specific to pipes. Nest building blocks can be globally scoped, controller scoped, method scoped, and the bonus 4th one, param scoped, which, as we said, is available to pipes only. Note that these different binding techniques give you granularity and control at different levels in your application. Each one does not override another, but rather layers each one on top. So be careful in how you implement these. For example, if you have a globally scoped pipe, it will be applied as well as any other you might add, whether it's controller scoped, method scoped, etc. So far in this course, we've already seen globally scoped pipes in action when we use the validation pipe to help us validate incoming request payloads, amongst other things. If we open up our main TS file, we'll see that we previously bound the validation pipe globally by calling the useGlobalPipes method of our app instance. You can see that if we type app.use, IntelliSense shows us corresponding methods for every other building block available here, respectively useGlobalPipes, useGlobalGuards, useGlobalInterceptors, and useGlobalFilters. Going back to our validation pipe here, one big limitation of setting it up and instantiating it by ourselves like this is that we cannot inject any dependencies here since we're setting it up outside of the context of any Nest.js module. So how do we work around this? One option we have is to set up a pipe directly from inside a Nest module using the custom provider-based syntax we saw in earlier lessons. Let's open up our app module file and define something called the app pipe provider. This app pipe provider is a special token exported from the Nest.js core package. Providing validation pipe in this manner lets Nest instantiate the validation pipe within the scope of the app module, and once created, registers it as a global pipe. Note that there are also corresponding tokens for every other building block feature, such as app interceptor, app guard, and app filter. Back to our validation pipe. What if we don't want to use it globally, but somewhere more specific, like on a certain controller? Let's imagine that we want to bind a validation pipe to every route handler defined only within our Coffees controller. Let's open up our Coffees controller file and make use of a new decorator, Use Pipes, that we haven't seen yet. This Use Pipes decorator can be passed in a single pipe class or a comma-separated list of pipe classes. Just like in other scenarios, there are also corresponding decorators for every other building block that can be used here as well, named Use Interceptors, Use Guards, and Use Filters. Alternatively, you can even pass an instance of a class here. Take, for example, providing new validation pipe inside of the decorator. This is super useful when you want to pass in a specific configuration object to the validation pipe for this exact scenario. Note that as a best practice, try to apply filters by using classes instead of instances whenever possible. This reduces memory usage since Nest can easily reuse instances of the same class across your entire module. All building blocks can also be method scoped. Imagine that you want to bind a pipe to a specific route. We can achieve this by simply applying the same decorator we just saw, Use Pipes, but on top of the specific method we want to declare it on. Let's say we want to add specific validation to our getFindAll method within Coffees controller. With this set up, this validation pipe is only applied to this single findAll route handler. We are already familiar with the 3 different ways of tying filters, guards, pipes, and interceptors to our route handlers. But as we said, there is a 4th bonus way that's only available to pipes, and it's called param-based scope. Param-scoped pipes are useful when the validation logic concerns only one specific parameter. Let's scroll down to the update method here. This method takes 2 arguments, the resource ID as well as the payload required to update the existing entity. What if we want to bind a pipe to the body of the request but not the ID parameter? This is exactly where the param-based pipe comes in handy. By passing the validation pipe class reference directly to the body decorator here, we can let Nest know to run this particular pipe exclusively for just this specific parameter. And there we have it. With these 4 powerful building blocks, we can now control the flow, content, validation on anything in our application globally, all the way down to a specific controller, method, or even a parameter. Nest.js comes with a built-in exceptions layer responsible for processing all unhandled exceptions across our application. When an exception is not handled by our application, it is automatically caught by this layer, which sends the appropriate user-friendly response. Out of the box, this action is performed by a built-in global exception filter. While this base built-in exception filter can automatically handle many use cases for us, we may want full control over it. For example, we may want to add exception logging or return our errors back in a different JSON schema. Exception filters are designed for exactly this purpose. They let us be in charge of the exact flow of control and the content of the response being sent back to the client. Let's create an exception filter that is responsible for catching exceptions that are an instance of the HTTP exception class, and implement our own custom response logic for it. Let's get started by firing up our terminal and generating a filter class using the Nest CLI filter schematic by entering nestgfilter common/filters/http-exception. Note that we generated this filter in a common directory where we can keep things that are not tied to any specific domain. Let's open up the newly generated HTTP exception filter and see what we have inside. As you can see, the Nest CLI generated an example filter without any business logic, of course. The catch decorator on top binds the required metadata to the exception filter. This catch decorator can take a single parameter or a comma-separated list. This allows us to set up a filter for several types of exceptions at once if we wanted. Since we want to process all exceptions that are instances of HTTP exception, let's pass the HTTP exception class between the parentheses. All exception filters should implement the exception filter interface exported from nestjs/common. This interface requires that we provide the catch method with its indicated method signature. Also, we can see that our class accepts a type argument, which indicates the type of the exception argument in our catch method. Again, since we want to process all exceptions that are instances of HTTP exception, let's change this to T extends HTTP exception. Alright, with all of that set up, now we can implement our custom response logic. To do this, we'll need to access the underlying platform's response object so that we can manipulate or transform it and continue sending the response afterwards. So where do we get a hold of the original response? Let's use the second parameter here, host, which we can see as an instance of arguments host, and call the method switch to HTTP on it, saving this as the variable CTX, short for context. This switch to HTTP method gives us access to the native in-flight request or response objects, which is exactly what we need here. Next, let's use this CTX variable and call the getResponse method on it. This method will return our underlying platform's response. Remember, in Nest.js, this is expressed by default, but could also be swapped for Fastify. For better type safety here, let's specify the type as response, importing this type from the Express package. Now that we have our response, let's use the exception parameter available to us in this method and extract two things, the status code and body from the current exception. To get the status, we can simply call the getStatus method as we see here. Let's also get a hold of the raw exception response by calling the getResponse method and saving that to a variable as well. Since for demonstration purposes, we're trying to pass back this original error response, we need to do a little bit of work here. First, we need to test whether the response is a string or an object. If it's a string, we're going to create an object and put that string inside of the message property. Otherwise, we're all set, and our exception response is already an object. By doing all of this, our errors will now be fairly uniform, and we can spread this error variable into our final response, which we'll do in a moment. Great, so now that we have everything we need, let's start building our response back that we'll be sending. First, let's set the status code for the response we're going to send back via the status method. Lastly, we need to send the exception response back. Our application's underlying platform is Express, which is the default. There are several ways we could do this. In our case, let's just use Express's JSON method. We can simply chain this method after our status call as we see here, and using the spread operator, we can pass the original error from our exception inside of this JSON method. As of right now, our exception filter here isn't really doing anything unique yet. So let's pass in something custom here along with the original exception. This way we have something we can look for in all of our errors to make sure everything with the exception filter works. Let's add a new timestamp property and give it the value of new date to isostring. Great, now with all this in place, let's bind this global exception filter to our application. Since we don't need any external providers here, we can just bind this exception filter globally using the app instance in our main.ts file. Let's head over to the main.ts file and add it real quick with app-instance. guard.useGlobalFilters, passing in new HTTP exception filter inside. Now that everything's in place, let's test it out by triggering some API errors. Let's make sure that our app is running in our terminal, and if not, make sure we run npm run start:dev again. With our application running, let's open up Insomnia and perform a GET request to a non-existing resource and purposely make an error happen. Let's hit something like coffees/-1, where -1 is obviously an ID we don't have in the database. As we can see, the response came back with an error and clearly used our new custom exception filter, since the response contains our new timestamp property. Perfect. So naturally, this exception we created was a basic example implementation. But you can see that within this exception filter, we could have just as easily used some sort of logging service to track our errors, maybe even called an analytics API. Anything we'd want to do whenever an HTTP exception occurs in our applications. Guards have a single responsibility, which is to determine whether a given request is allowed access to something. If the request meets certain conditions, such as permissions, roles, ACLs, etc., it will be allowed access to that route. If the conditions are not met, then it will be denied and an error will be thrown. One of the best use cases for guards is authentication and authorization. For example, we could implement a guard that extracts and validates a token and uses the extracted information to determine whether the request can proceed or not. Since there are many different approaches and strategies to handle authentication and authorization, in this video we'll focus on a simplified example and learn how to leverage guards themselves in our projects. If you're interested in learning more about authentication itself, check out our separate course extension, which is particularly focused on the implementation of an enterprise-grade authentication feature and all of the complexities that go along with that. Alright, so to learn how guards work conceptually, let's create a guard that is responsible for two things: validating whether an API key is present within an authorization header, and secondly, whether the route being accessed is specified as public. Let's call this new guard API Key Guard. Let's fire up the terminal and generate a guard class using the Nest CLI. Let's enter in nest gguard common/guards/API-key. Note that we generated this guard in the common directory where we can keep things that aren't tied to any specific domain. Alright, so let's open up this newly generated API Key Guard file and see what we have inside. As we can see, the Nest CLI generated an example guard for us, without any logic inside, of course. Similar to providers, a guard is just a class with the injectable decorator, which we've seen in previous videos. One important requirement of guards is that they should implement the CanActivate interface exported from Nest.js Common. This interface requires us to provide the CanActivate method within our class. This CanActivate method should return a Boolean, indicating whether the current request is allowed to proceed or denied access. This method can also return a response that's either synchronous or asynchronous, such as a promise or observable. Nest will use the return value to control the next action. If it returns true, the request will be processed. If it returns false, Nest will deny the request. Looking at the example code the Nest CLI generated for us here, we have return true hard-coded for now. This means that currently every request will be allowed to proceed. Just for testing purposes, let's change this line to return false, indicating that every request should be denied access. And now that our initial mock guard is all set, let's bind it to our application globally. Let's open up the main.ts file and add app.useGlobalGuards, passing in our new API Key Guard inside of it. Great. Let's make sure that our application is running in the background, and let's navigate to Insomnia and test any endpoint. As we can see, all of our endpoints now respond with status 403, forbidden resource. Just as we expected, it worked perfectly. But right now, our guard is not programmatically determining anything about our route or the caller yet. It's simply always returning false. That doesn't make much sense, right? Instead, let's set up our guard to handle the scenario we talked about in the beginning of this lesson, which is to validate an API key that should be present within each request, but only on routes that are not specified as public. So how can we get started here? Well, first, let's define this API key that we're talking about. To make sure that we never push this secret key to our Git repo, let's define the API key as an environment variable. Open up our .env file that we created in a previous lesson, and let's add the following API_key line. The API key here is just a random generated string, so feel free to use whatever you'd like for this example. With this in place, let's head back to our guard. Here in our guard, we want to retrieve the API key from any incoming request that is not labeled as public. We'll be handling this public part in a moment. For our API key, let's assume that the caller is passing this key as an authorization header. To get the information about this incoming HTTP request, we'll need to access it all from the execution context, which inherits from arguments host, which we've already familiarized ourselves with when we used it with the exception filter. We can actually use those same helper methods from before, but this time to get the reference of the request object instead of the response. This switch to HTTP method gives us access to the native in-flight request, response, and next objects, which is exactly what we need. Next, we need to call the getRequest method on it, which will return our underlying platform's request wrapper object. Remember, in Nest this is expressed by default, but it could also be swapped for Fastify. For better type safety here, let's specify the type as request, importing this type from the express package again. Now let's use this request object to retrieve the authorization header from each request, if it's even there. Lastly, let's compare the authorization header passed in with the registered API key we have stored in our environment variable. For now, we'll simply access the environment variables using the process.env object, but ideally you'd want to leverage the config service instead. With all of this in place, let's open up Insomnia and test any endpoint in our application and see if our guard works so far. As we can see, our application responded with the status 403 forbidden resource. Since we didn't pass in any authorization header, especially one with our specific API key, it looks like our guard's working perfectly. Let's try this same API request again, but this time, let's add an authorization header with the correct API key. With this in place, let's hit send and call the endpoint again. Perfect. We got a 200 response back and no error this time. Our guard was able to verify that the authorization header matched our secret API key, and we were allowed access to continue the API request. So far, we've finished setting up the API key validation functionality we wanted, but we still aren't checking whether the specific route being accessed is public or not. In the next chapter, we'll look at how metadata and a few other Nest features can help us achieve just that. In the last lesson, we implemented the first goal for our new guard, which was to verify whether an API token is present when a route is accessed. In this lesson, we'll be looking at how we can complete the next piece of functionality we needed, which was to detect whether the route being accessed is declared public or not. But how can we declaratively specify which endpoints in our application are public, or any data we want stored alongside controllers or routes? This is exactly where custom metadata comes into play. Nest provides the ability to attach custom metadata to route handlers through the setMetadata decorator. The setMetadata decorator takes two parameters. First being the metadata key that will be used as the lookup key, and the second parameter is the metadata value, which can be any type. This is where we'd put whatever values we want to store for this specific key. So let's put this to use to learn how it all works. Let's open our Coffees controller file, head over to our findAll method, and add this setMetadata decorator on top. making sure it's imported from the nestjs/common package. Inside the decorator, let's pass those metadata key and value parameters. For our key, let's enter the string of isPublic. For our value, let's enter a boolean of true. This is the most bare-bones way of setting up metadata on a route, but it's not actually the best practice. Ideally, we should create our own decorator to achieve the same result. This is a much better practice because we will have less duplicated code, we can reuse the decorator in multiple places, and a custom decorator gives us much more type safety. Let's improve our existing code and make our own decorator and call it public. First, let's create a new folder within the common directory and call it decorators. Here we can store any other future decorators we might make. In this folder, let's create a new file called public.decorator.ts. In this file, we're going to export two things. One being our metadata key, and the other being our new decorator itself that we're going to call public. For our key, let's export const isPublicKey and set it equal to the string of isPublic, just like we called it previously. The benefit of exporting this variable here is that anywhere we might look up this metadata, we can now import this variable instead of using magic strings and accidentally mistyping the name. Now let's export our decorator by entering export const public and setting this equal to an arrow function that returns set metadata. Inside of set metadata, just like before, we need to pass in that key and value. So let's use our isPublic key variable. And for the value, let's pass in the boolean of true, just like we did previously. And that's it. We just made our first decorator. Next, let's swap out the code we previously added in our copies controller to use our new decorator. Let's head back over to that findAll method signature and replace the previously added setMetadata expression with this public decorator, making sure to import it from our local directory. Perfect. We now have a much more future-proof and easily reusable decorator that we can use throughout our entire application if needed. Let's tie everything together and fix up that API key guard to use it. Currently, our guard returns true or false depending on whether the API key was provided with the request. But now we need to add our isPublic logic here. We need the guard to return true when the isPublic metadata is found before continuing further and testing whether an API key is present. In order to access the route's metadata in our guard, we'll need to use a new helper class called Reflector. The Reflector class allows us to retrieve metadata within a specific context. This class is provided out of the box by the Nest framework from the Nest.js core package. Let's inject the Reflector class here inside of our constructor. Now we can use this provider within the canActivate method to retrieve the metadata of our handler. Let's add a new variable called isPublic. For this variable, let's utilize this.reflector.get, which looks up metadata by its key. In our case, the exported variable isPublicKey we just made a moment ago. Reflector requires a target object context for the second parameter. In our case, we want to target the method handler in our given context. So let's pass in context.getHandler. Just for reference, if you needed to retrieve metadata from a class level, you'd call context.getClass here instead. For more information on Reflector and other possibilities here, read more about it in the Nest.js documentation. Okay, great. Now that we have the value from our decorator inside of our guard, there's one last thing we need to do. If a route is public, we can simply skip the validation of the API key. Let's add a simple if statement And if isPublic is true, let's just return true. And lastly, we mentioned earlier that we shouldn't use process.env directly, so let's fix that and instead use the config service. Let's move into the constructor real quick and inject config service. With this service injected, we can now replace the previously used process.env.api key call with this.configService.get, passing in the string of API_key. Let's save all of our changes and check the terminal to make sure everything is compiling correctly. Okay, so our guard is ready, but it looks like the application couldn't bootstrap properly and it is throwing some compilation errors. Well, what happened? Well, these errors appeared because we're using dependency injection inside of our guard, which was instantiated in the main.ts file. So how can we fix this? As we showed in previous lessons, global guards that depend on other classes must be registered within a module context. Let's fix this real quick and add this guard to a module. And actually, let's take it up a notch and create a new module for our common folder, and we can instantiate our guard there. Let's fire up another terminal window, and let's generate a module and call it common with nestgmo common. This will generate a module class where we can register any global enhancers we might make in the future, including our API key guard. Great, so let's open up this new module and utilize the custom provider setup we learned in a previous lesson. This is where we pass in an object into our providers array, providing a specific class or key, and then the value to be used for it. Inside of our module decorator, let's add a providers array and pass in an object with provide app_guard and use class with our API key guard. This setup is very similar to using use global guards that we had in our main.ts file, but as we said, that option is only available if our guards do not use dependency injection. Note that there is a way around that, but it isn't a best practice since you'd have to manually pass in dependencies. One last thing here, let's make sure to import the config module in an imports array here, so we can use the config service in our guard. Now let's open up our main.ts file and remove that use global guards line since we don't need it anymore, and save all of our changes. Let's switch to our terminal window again to make sure everything can bootstrap properly now. Great, everything's compiling again. Now let's open up Insomnia and put our new guard to the test. Let's start by removing the authorization header and make a get/coffees request, which we set up to use our public decorator. If everything works as expected, it should not return a 403 error since our guard should allow access to it. And it worked great. Next, let's try a route that doesn't have the public decorator, like a get request to the endpoint coffees/1. Our guard should deny us access to this route since it is neither public nor are we passing in an authorization header. And there it is, 403 forbidden. Our guard works perfectly. So to wrap up, we covered a lot of ground in this lesson, tapping into a lot of concepts we learned in previous lessons. Now we have the additional power to create our own decorators and utilize handler metadata, useful for anything our application might need in the future. Interceptors have many useful capabilities inspired by the aspect-oriented programming technique. This technique aims to increase modularity by allowing the separation of cross-cutting concerns. Interceptors achieve this by adding additional behavior to existing code without modifying the code itself. Interceptors make it possible for us to bind extra logic before or after method execution, transform the result returned from a method, transform the exception thrown from a method, extend basic method behavior, or even completely overriding a method, depending on a specific condition. For example, doing something like caching various responses. Alright, so to learn how interceptors work conceptually, let's run through an example use case where we always want our responses to be located within a data property and create a new interceptor to handle this for us. Let's call this new interceptor Wrap Response Interceptor. This new interceptor will handle all incoming requests and wrap our data for us automatically. To get started, let's generate an interceptor class using the Nest CLI by entering nestginterceptor common/interceptor/wrap-response. Note that we generated this interceptor in the common directory like we have many times before, since this interceptor isn't tied to any specific domain. Let's open up this newly generated wrap response interceptor file and see what we have inside. The Nest CLI generated an example interceptor for us, without any business logic. Similar to providers, an interceptor is a class with the injectable decorator. All interceptors should implement the Nest interceptor interface exported from Nest.js Common. This interface requires that we provide the intercept method within our class. The intercept method should return an observable from the RxJS library. If you're not familiar with RxJS, it is a library for reactive programming using observables, making it easier to compose asynchronous or callback-based code. RxJS itself is outside of the scope of what we can dive into here. Just know that it's a powerful alternative to promises or callbacks. Back to our code. The call handler interface here implements the handle method, which you can use to invoke the route handler method within your interceptor. If you don't call the handle method in your implementation of the intercept method, the route handler method won't be executed at all. This approach means that the intercept method effectively wraps the request response stream, allowing us to implement custom logic both before and after the execution of the final route handler. Alright, so we've covered a lot of theory so far. Let's add some console logs to see where interceptors fit in the request response lifecycle. Since we've called console log before calling the next handle method, our before message should appear in the console before the actual route handler is executed by the framework. Since handle returns an RxJS observable, we have a wide choice of operators we can use to manipulate the stream here. In this example, we're using the tap operator, which invokes an anonymous logging function upon graceful termination of the observable stream, but doesn't otherwise interfere with the response cycle at all. The data argument of the arrow function we passed into the tap operator here is in fact the response sent back from the route handler. Basically, think of this as whatever comes back from our endpoint. Here, we're just doing a console log to say after, and logging that data back as well. To test it all out, let's bind this interceptor to our application globally. Let's open our main TS file and add app.useGlobalInterceptors, passing in new wrap response interceptor. Great. Now, let's make sure our application is running in the background, and let's navigate to Insomnia and test any endpoint in our application. First, let's make sure we have some coffees stored in our database. To do so, let's hit the post coffees endpoint and add a random coffee. Perfect. Now let's hit the get/coffees endpoint and switch back to VS Code to see those console logs in the terminal. As we can see, before was logged and then after, followed by the actual value from our findAll method, which represents the coffees endpoint. It looks like our interceptor worked. Let's open up Insomnia again and test another endpoint. Let's test coffees/1 this time. This time, we should see a single object following the after log in our terminal. Great, so far so good. So now that we can see how interceptors work and their part in the request response lifecycle, let's implement our data wrapper idea we talked about at the beginning of this lesson and wrap our responses inside of a data property. To do this, let's replace the tap function with the map operator. The map operator takes a value from the stream and returns a modified one. Since we wanted to wrap all responses in the data property, let's return an object with a key value of data. Every time this map function is called, it returns a new object with a data property filled with our original response. Remember, everything we've done here is mainly for demonstration purposes, but hopefully now you can see the power of interceptors and how there's a potential to do so many other things here, like passing down version numbers, analytics tracking, etc., etc. Alright, so let's save all of our changes, open up Insomnia, and test out this interceptor. Let's execute any HTTP request and see what the application sends back to us. Perfect. As we can see, the response was automatically wrapped in an object within the data property. So wrapping up, in this video, we've shown how interceptors give us an incredible power to manipulate requests or responses without changing any underlying code. So far, we've learned how to use interceptors to bind extra logic before and after method execution, as well as automatically logging and transforming results returned from route handlers. Another technique useful for interceptors is to extend the basic function behavior by applying RxJS operators to the response stream. Let's see this in action with a realistic example. To help us learn about this concept by example, let's imagine that we need to handle timeouts for all of our route requests. When an endpoint does not return anything after a certain period of time, we need to terminate the request and send back an error message. Let's start by generating another interceptor, naming it timeout, and also placing it in the common interceptors folder. Let's open up this newly generated timeout interceptor and add some logic in there. In our example, we want to terminate a request after a specific period of time. So let's use the timeout operator imported from RxJS/operators to achieve this. To demo this easily, let's set a very quick timeout of 3000 milliseconds. This means that when a request is made, after 3 seconds, the request processing will be automatically canceled for us. To test it out, let's bind this second interceptor to our application globally, and since it has no dependencies, we can add this in our main.ts file. So let's add our new timeout interceptor here in our useGlobalInterceptors method. Note that we can actually bind multiple interceptors here simply by separating them with commas. Now, to make sure that our interceptor works properly, let's open up the Coffee controller file and temporarily add a setTimeout function in our findAll method to simulate a very long delay. Let's set a timeout for 5 seconds higher than the 3 seconds we set in our interceptor to purposely trigger our timeout interceptor. Perfect. Now let's open up Insomnia and execute this endpoint by making a request for get/coffees. As we can see, after 3 seconds, we received a 500 error, which means our timeout interceptor worked. However, the error message we got back is not really descriptive. It says internal server error, but how could we make this message more user-friendly? Heading back to our timeout interceptor again, let's chain another operator called catchError inside of our pipe method. The RxJS catchError operator allows us to catch all exceptions that occurred within the stream. In the callback function we provide here, we can check if the error thrown is an instance of timeout error, which is also imported from RxJS. If so, we use a utility function, throwError, from RxJS to create a stream which immediately emits an error for whatever is passed into it. Since we want our error message to be more specific for this scenario, let's use a Nest.js class called requestTimeoutException imported from Nest.js Common, so we can throw the correct error message back to our users, letting them know the request has actually timed out. Great, so let's save our changes, navigate back to Insomnia, and test the endpoint once again. As we can see, this time we received the 408 response with the descriptive message request timeout. So in this lesson, we learned how to add additional superpowers to our interceptors along with some new tricks from RxJS all which are very common scenarios and helpful in most of our Nest.js applications. Pipes have two typical use cases: transformation, where we transform input data to the desired output, and validation, where we evaluate input data and, if valid, simply pass it through unchanged. If the data is not valid, we want to throw an exception. In both cases, pipes operate on the arguments being processed by a controller's route handler. Nest.js triggers a pipe just before a method is invoked. Pipes also receive the arguments meant to be passed on to the method. Any transformation or validation operation takes place at this time. Afterwards, the route handler is invoked with any potentially transformed arguments. Nest.js comes with several pipes available out of the box, all from the Nest.js common package. For example, validation pipe, which we've seen in previous lessons, and parse array pipe, which we haven't seen, but it's an extremely helpful pipe that helps us parse and validate arrays. To learn how we can build our own custom pipes, let's create a pipe that automatically parses any incoming string to an integer, and let's call it parseInt pipe. Nest already has a parseInt pipe that we could use from the Nest.js common library, but let's create this basic pipe for learning purposes to help us fully understand the basic mechanics of a pipe. Let's fire up the terminal and generate a pipe class using the Nest CLI pipe schematic, placing it in the common/pipe folder and calling it parse-int. Note that we generated this pipe in the common directory again, where we can keep things that aren't tied to any specific domain. Let's open up this newly generated parseInt pipe file and see what we have inside. As we can see, the Nest CLI generated an example pipe for us without any logic inside. Similar to providers, a pipe is a class with the injectable decorator. But all pipes should implement the pipe transform interface exported from Nest.js Common. This interface requires us to provide the transform method within our class. This transform method has two parameters: value, the input value of the currently processed argument before it is received by our route handling method, and metadata, the metadata of the currently processed argument. Whatever value is returned from this transform function completely overrides the previous value of the argument. So when is this useful? Consider that sometimes the data passed from the client needs to undergo some change before this data can be properly handled by the route handler method. Another example use case for pipes would be to provide default values. Imagine if we had some required data fields that were missing. We could automatically set these defaults within a pipe. Transformer pipes can perform these functions by interposing the transformation function we create between the client request and the request handler. This is merely another example, but the point is to show that there are many powerful things you can do with pipes. Alright, so back to creating a custom parseInt pipe. Let's start by implementing the actual logic. First, we can assume that the input value, or value, is a string, so we can change the type from any to string. Next, let's use the built-in parseInt JavaScript function to try parsing the input string to an integer. Let's add some conditional logic here in case we see any errors. If the return value is not a number, we can make sure to throw a bad request exception. Otherwise, we can return the modified value, which is now an integer. Perfect. With this in place, we can now bind our pipe to some param decorators. Let's open up the coffees controller file and navigate to the find_one method. Before we do anything here, let's add a single console log to log the ID argument's value. Now let's navigate to Insomnia and execute a GET request to the coffees/abc endpoint. Note, we're going to pass abc a string instead of a number like 1 or 10. Let's switch to VS Code and fire up the terminal and see what was logged. As we can see, it outputs NaN, or not a number. This means that although our ID abc could not have been parsed to a number, the find1 method was called with an incorrect argument. To prevent situations like this, let's use our newly created parseInt pipe to validate the incoming parameter, and in case it's not parsable to an integer, our pipe will automatically throw a validation exception for us. So let's pass in our parseInt pipe as the second parameter to our param ID here, save our changes, and test the endpoint again. Great, as we can see, this time we received a 400 error with the message stating that validation failed. As we said, Nest comes with this pipe already, but hopefully this example showcases the power of pipes and how you could implement your own to do a multitude of useful processes for your application. Middleware is a function that is called before the route handler and any other building blocks are processed. This includes interceptors, guards, and pipes. Middleware functions have access to the request and response objects and are not specifically tied to any method, but rather to a specified route path. Middleware functions can perform the following tasks: executing code, making changes to the request and response objects, ending the request-response cycle, or even calling the next middleware function in the call stack. When working with middleware, if the current middleware function does not end the request-response cycle, it must call the next method, which passes control to the next middleware function. Otherwise, the request will be left hanging and never complete. So how can we get started creating our own middleware? Custom Nest middleware can be implemented in either a function or a class. Function middleware is stateless. It cannot inject dependencies and doesn't have access to the Nest container. On the other hand, class middleware can rely on external dependencies and inject providers registered in the same module scope. In this video, we'll focus on building a class middleware, but remember, you can always use functions to create them as well. Let's fire up the terminal and generate a middleware class using the CLI, and let's call it logging. Note that we generated this middleware in the common directory again, since it isn't tied to any specific domain. Let's open up this newly generated logging middleware file and see what we have inside. As we can see, the Nest CLI generated an example middleware without any logic inside. Similar to providers, a middleware is a class with the injectable decorator. All middleware should implement the Nest middleware interface exported from nestjs/common. This interface requires us to provide the use method within our class. This method does not have any special requirements. Just remember to always call the next function, otherwise the request will be left hanging. For now, we'll keep things simple. Let's just add a console log before invoking the next function to see how middleware fits into the request-response lifecycle. With this in place, we can now register our newly created middleware. As we've mentioned earlier, middleware aren't specifically tied to any method. We can't bind them in a declarative way using decorators. Instead, we bind middleware to a route path represented as a string. To register our logging middleware, let's open up our common module file. First, let's make sure that our common module class implements the Nest module interface. This interface requires us to provide the configure method, which takes the middleware consumer as an argument. The middleware consumer provides a set of useful methods to tie middleware to specific routes. Just to test it out, let's apply the logging middleware to all routes using the asterisk or wildcard operator. To add our middleware, let's call the apply method on consumer, passing in our logging middleware, and then let's call the forRoutes method, passing in the wildcard asterisk. Let's save our changes and navigate to Insomnia and perform an HTTP request to any endpoint. Let's go back to VS Code and see if anything popped up in our terminal. Great, we can see hi from middleware string in our console. Now, taking a step back to our middleware consumer, there are several other ways of tying middleware to different route paths. So far, we've bound the logging middleware to every route using the asterisk wildcard, but we could also apply it only to routes with, let's say, the coffees prefix if we want. We can even restrict middleware further if we'd like, let's say to a particular request method, like only for get methods, by passing an object containing the route path and request method like so. Note that we imported the request method enum we used in previous lessons to reference the desired request method type. Lastly, we can also exclude certain routes from having the middleware applied with the exclude method. This method can take a single string, multiple strings, or a route info object identifying routes to be excluded. For example, we can apply the middleware to every route except for those with the coffees prefix if we wanted. Now that we've looked at a few of the options available to us here, let's revert back to our original for-routes wildcard since we want to bind the logging middleware to every existing endpoint for now. Let's open up the logging middleware file again and add some additional functionality in here. For a fun example, let's calculate how long the entire request response cycle takes by using console.time. Note that this calculation will include the interceptors, filters, guards, method handlers, etc. that this route may have as well. In this example, we're hooking into the Express.js response finish event so we know when our console time end should occur. Let's save our changes and navigate to Insomnia. Now let's execute a random HTTP request to our application and head back to the terminal. As we can see, there's a new request response message indicating that the full round trip took roughly 23 milliseconds. This was all a basic example, but hopefully this shows you the potential that middleware brings to an application. For a more realistic use case, you could potentially utilize something like what we just created to log long-lasting methods to a database and keep track of how long every API takes to complete. A lot of Nest.js is built around a powerful TypeScript language feature called decorators. Decorators are simply functions that apply logic. Nest.js provides a set of useful param decorators that you can use together with the HTTP route handlers, for example, body, to extract the request body, or param to pick a specific request parameter. Additionally, we can create our own custom decorators. Let's imagine that for some reason, we want to retrieve the request protocol from within the route handler. Normally, we would need to inject the entire request object with the rec decorator into the method definition. However, this makes this particular method harder to test since we would need to mock the entire request object every time we try to test this method. In order to make our code more readable and easier to test, let's create a custom param decorator instead. To get started, let's open the common/decorators folder and create a protocol.decorator.ts inside. Now, inside of this file, let's make use of the utility function createParamDecorator imported from Nest.js Common to build our custom decorator. Since we're trying to find the request protocol for our decorator, we're going to need to retrieve it from the request object. We can retrieve this from the execution context we've seen in previous lessons with switch to HTTP and then calling getRequest. Afterwards, let's simply return request.protocol and we're all set. Great. Now to test our decorator, let's open up our coffees controller file and temporarily use it on the findAll method. Let's add a single console log within the method to log out this protocol parameter and see what it gives us. Let's just save our changes, navigate to Insomnia, and execute a get/coffees request to see everything in action. Now let's head back to VS Code and fire up our terminal. We could see HTTP, our protocol, was logged in the console. Great, it works. We can also pass arguments to our custom decorators if needed. In this instance, our protocol decorator is fully stateless, so there's no reason to pass in any parameters since there's nothing to configure. However, in more sophisticated scenarios where the behavior of our decorator depends on different conditions, we can pass the data argument into them. For example, let's say that we wanted to pass a default value to the decorator we just made. Let's just pass a string of HTTPS between the protocol parentheses. To access this value from within our param decorator factory, we can use the data argument, the first argument here we previously hadn't touched. To make our decorator more self-explanatory, let's change the argument name to default value and set it to type string for better readability and type safety. With this in place, now let's see if these values are actually coming into our decorator and add a single console log to log out this default value to our terminal. Again, let's make sure to save our changes, navigate to Insomnia, and execute this same get/coffees request. Back over to our terminal again, we can see the default value HTTPS object was logged in the console. Great.